Hey guys, Major Math here with a fluid mechanics lesson. The point of these lessons is to give a quick rundown for what to expect in the example problems. If you have any questions, leave it in the comments, and if you need help with other problems, I left my email in the description. Without further ado, let's get started. Question 2.77 says calculate the maximum capillary rise of water between two vertical glass plates spaced 1 millimeter apart. Okay, first step is always write your goal. Find max capillary rise. We're going to make this variable this, change in height. This will be how much the water will rise. And it says between two vertical plates spaced 1 millimeter apart, so that's our given. Spaced at 1 millimeter apart. That equals, if we convert that to meters, be right divided by 1,000, right? Okay. We're gonna have to assume it doesn't give us a temperature of the water. We're gonna assume that the temperature of the water is 15 degrees Celsius because we're gonna need to know the specific weight, and this is a problem dealing with surface tension, so we're going to need to know the surface tension as well. Let's go ahead and write that down because we'll need it later. So if you look in the textbook, table F.4 says, oh, that's properties there, right here. F.5 says that specific weight is 9,800 newtons per meter cubed, and that surface tension is 0.073 newtons per meter. So let's go ahead and write that down. Therefore, specific weight is 9,800, and surface tension is 0.073. Okay. So let's draw this out. Let's see what we're looking at. So I'm gonna drastically make this bigger than 1 millimeter. Alright, so we have so this is spaced out 1 millimeter. These are our two glass plates. This is our water that it's in. And then we know that the water is going to rise up and kind of look like this, right? This is under a microscope, that's why it's so big. Alright, and then we're going to need to find this right here, right? That's the change in height. This is how much it rises between the original water level. Okay, so we know this formula. Force equals surface tension times length of the wetted perimeter, okay? And we also know that force of the weight is equal to mass times gravity, okay? So, and then we have this right here. We know that from what we know in statics, and this is in equilibrium, right? This is what it's going to look like with that, like at any moment in time when you have these two walls. So we know that the force of surface tension is going to equal the force in weight, right? So we gotta, I'll do this too. We know we can plug this in right here, and we can plug mg in right here, right? And before we do that, let's rearrange, because we gotta find, like, we don't know where we're gonna, how do we find height from this? How do we implement the variable height into these equations that we know we gotta use? So we gotta do some rearranging. So let's rearrange this weight one first, right? So let's look at mass. How do we rearrange this mass to get height involved, or this force of weight? So we know that density equals mass over volume. We can rearrange that to density times volume equals mass, right? So let's go, and then we'll just go ahead and rearrange the volume, right? So we know from the volume we can get the variable height from it. So let's rearrange it again. and say that volume is equal to length times width and height, right? Because we're dealing with a rectangle here. So length times width times the change in height, right? So now you can see where we're getting this variable height from, and we can actually end up solving this. And this equals mass, okay? So let's plug this in for mass. So rearrange this to density times length times width times height times gravity. Okay, and then we need to rework this to make this represent the wetted perimeter. So when we're looking at this, what is going to be the wetted perimeter? So it's just two walls. There's nothing like in front. We're not taking a cross section and looking at this. It's really just those two walls. So the perimeter is just going to be the length of the whatever, how deep this goes back. See what I'm saying? That's going to be the length. So we're just, this is just going to be, is just going to equal, the wetted perimeter is just going to be 2 of the lengths, right? Because it's just 2 walls. So let's go ahead, and this is the main equation we're looking at. Let's plug this in for there, and let's plug in this right there. Let's go ahead and do that. Density times length times width times height times gravity. We see that we have a length on both sides, so we can actually go ahead and cancel it out. So we end up not needing to know the length, which is useful. We know the width, right? It's separated by 1 millimeter apart. So we know that this is that 1 millimeter or 0.001 meters. And then we know density from the textbook. It's up here, written right there. Oh, no we don't. Do we need density? We might need density. No, we don't need density. We could use density of this, but we can also do, we know that specific weight is density times gravity, so we can actually just rearrange this to look like right, because specific weight equals density times gravity, so we can just replace this density and gravity with just specific weight. That's what I did in my notes, sorry about that. And then and we need to solve for the change in height, so let's rearrange this to solve for change in height. Right, I did that backwards, didn't I? Right, so I just divided by specific gravity, and the width, moved it over. Okay, so we're left with this formula, and we can go ahead and plug everything we know. So this will equal 2 newtons per meter over specific weight, 900. Width is 0.001 meters. And change in height, if you put that in the calculator, we'll get 0.015 meters. Multiplied by 1,000, it's 15 millimeters. So the max capillary rise will be 15 milliliters. Thanks for watching, soldiers. Don't forget to leave a like and subscribe for more content like this. If you have any questions, leave it on the comments, and if you need help with any other problems, feel free to contact me with the email shown on the screen.